Welcome back to our series on statistical methods. I'm Mark Ledbetter. This is lecture 29, part B, and we are in part 4 of linear regression, and this is chapter 10. So let's go ahead and get started. In this video, we're going to finish up this section of the chapter on simple linear regression, or straight line regression. So we need to talk about inferences, a couple of inferences or confidence intervals. And this may be a little confusing. We have two different types of confidence intervals. So the first one is talking about a confidence interval or inference about the regression line or the mean response. Remember that the regression line represents the mean response, okay? Expected or mean response, y, for each value of x. And we wish to construct a confidence interval for that regression line, specifically for some given value of x sub naught. Let's construct a confidence interval for mu of y given x naught. So about that mean value. This can be written as y hat of x naught. And we write out the regression equation, beta naught hat plus beta 1 hat x naught. And then we substitute in the expression for beta naught hat. And if you remember, we can regroup, and it's y bar, this quantity is y bar minus beta 1 hat times x bar. And so we substitute that in and regroup by beta 1 hat, and we get this expression. So we want to take the variance of this, because we need the standard error of the estimate in order to construct a confidence interval. So we take the variance of this, which is the variance of this last equation that we had, and because our covariance between yi and beta 1 hat is 0, we just end up with the variance of these two quantities. Now notice that x, recall that x is a fixed quantity here, so this is basically a constant. So when we take the variance of a constant times a random variable, we pull the constant out and square it. And that's exactly what we've done here. And the variance of y bar, the variance of a sample mean, is sigma squared over n. And so we substitute that in for the variance of y bar. We have x naught minus x bar, quantity squared, variance of beta 1 hat. Let's substitute in beta 1, the variance of beta 1 hat here. Notice that we have a sigma squared here, and here we can factor it out. And we have 1 over n plus x naught minus x bar squared over the sum of xi minus x bar squared. So this is our variance. But we have this unknown population parameter in here, and we need to estimate this variance. And we do that by plugging in the estimate for our sigma squared. And that estimate is right here, s sub y given x squared, okay? And notice that we have this extra hat now over the v for the variance. We had the hat where we were doing the variance for this y hat, or this fitted value, y hat x sub naught, sub x sub naught, hard to say. And we're giving this expression, so the symbol is going to be s squared sub y hat given x naught. And so we simply plug in the estimate for sigma squared, which is also the MSE, is another way of writing that, okay? Or actually, let's see, I think we put MS sub E. And so we plug that in, now we have the estimate. So now we have the standard error of the estimate, and that is multiplied by the t statistic with n minus 2 degrees of freedom, because that's the degrees of freedom of the sum of squares error. So we have our confidence interval formula here, y hat x naught plus or minus t times s sub y hat given x naught. Okay, so that's one of the confidence intervals. Now let's talk about predicting a new value of y at x naught, and we want a confidence interval for this single value, okay? And so the variance of our error of predicting an individual value y that is going to be the variance of y x naught minus y hat x naught. This is the residual, y minus y hat at x naught. So again, we have that the covariance is 0, so it's nice that we come out with variance of y sub x naught plus variance of y hat sub x naught. Variance of y is just sigma squared, and then we have our variance of y hat, so we're adding sigma squared to our previous, so we just figured this out above, that variance, and so we're basically adding sigma squared to that. So sigma squared is always greater than 0 or equal to at the worst. So the variance of an individual value is always larger than the variance of the mean value. Okay? So once we factor out sigma squared from both of these, we have a similar looking variance as we did here. Up here, we had a 1 over n plus this quantity. Now we have a 1 plus 1 over n and this quantity. So that's the difference, is that 1, okay? Which is, overall, that's the value of sigma squared that's being added to our variance estimate. So it's bigger. So notice that, and here's the what I just said, written down, that the variance of predicting a single value is always larger than the variance of the regression line. Excuse me. So the estimated variance, we're going to give this a S sub y pred given x naught, so that we have some way of differentiating this notation. All right, and so by estimating the variance that we just found up here, this is not an estimated variance, that's the variance. We estimate this by plugging in the estimate for sigma squared here. All right, and so then our confidence interval becomes y hat sub x naught plus or minus t with the degrees of freedom for error, n minus 2, and S sub y sub pred given x naught. All right, that's it for this video. If you have questions, please make sure you come to virtual office hours. If you need help prior to office hours, by all means email me. But when you email me, if it's about a problem, then email me what the problem is, because I may not have it available, and then your work on that problem so far. If it's code, then by all means send me a copy of the code, and in the email tell me where you're having the problem and that you need help. And I will get back to you as soon as it's possible. Please take care of yourself and stay safe, because we want to see you here next time.